Now let's look at the working of the Newton's rings. So this is also about an interference pattern, but there are some peculiarities regarding this pattern. So the apparatus is same as that of the air wedge. We have a convex lens, a monochromatic source, and with the help of these two we can derive some parallel rays of light. With the help of this glass plate we can ensure that these rays are normally incident on this lens and glass arrangement, and the pattern which is formed over here due to the interfering rays can be observed with the help of a traveling microscope. But the difference here is that instead of using two glass plates, here we use a plain glass plate and a planar convex lens with the convex part touching the plain glass. So when you look at this figure, here also you can imagine the presence of a thin film. Where is it happening? Between the space that is there between this glass plate and the convex lens, there is the presence of the thin film. So just like the earlier case, this can be any fluid. It can be air or it can be oil or some other fluid. So similar to the other case, there will be rays of light which is getting reflected from the top part of this film and also from the bottom part of this film, which will interfere to create a pattern. So here also we will be using the cosine law, where we can manipulate the thickness part to find the interference pattern conditions. So here at the center the glass plate and the lens is touching. So there is no thin film, the presence of thin film at this central point. And as we go outwards, the thickness of the film goes gradually increasing. But this is in a circular way. If you just imagine this in three dimension, if you look from the top part, the same thickness part will be in the form of a circular shape. Because if I consider the endmost part, the locus of all the end points will be a circle. Similarly, if I consider a point somewhere in between, the locus of all the points having the same thickness will be a circle. Now let's start from the beginning, like from the central part. If we look at the center, there is no film. But even there, light is getting reflected from the bottom part and the top part. And between these two rays, there will be a path difference of lambda by 2 or a phase shift of 180 degree. So these two rays will be interfering destructively, which we already know that any two rays which have a path difference of lambda by 2 will always interfere destructively. So always at the center or the central band or the central fringe in Newton's ring will be a dark fringe, because the rays from this part will be interfering destructively. And as we go outwards towards this film, how can we know how the rays are interfering? We have to measure the path difference. And the path difference formula we already know from the cosine law, that is delta x equal to 2 mu t cos r. And just like the air wedge case, there is a ray getting reflected from the top part, suffers no phase change, but there is another ray which is getting reflected from the bottom part, which will suffer a path change of lambda by 2, which has to be taken into account. Now what we have to do? Now what we have to do is substitute the value of delta x for constructive and destructive patterns. So let us now first consider the constructive case. For constructive interference, so here also, since it is a normal incidence phenomenon, r can be limited to 0. So cos r value will be 1. So this equation can be written as 2 mu t cos r will be 1 plus lambda by 2 will be equal to, what will be the value of delta x for constructive interference? For constructive interference, this will be n lambda, and 2 mu t will be n lambda minus lambda by 2, which is n minus half into lambda. So I am retaining this 2t over here and bringing all of the things to the right hand side, that is n minus half lambda on the right hand side, and I have to bring this mu to this side. So retaining this mu is your choice, because if this wedge, or if this space is filled with air, the refractive index will be 1. So you can omit this part, but that is your choice, because if it is not air and if it is some other liquid, this mu value will become handy. So I am retaining this 2t. Why did I do this? Earlier in the air wedge case, what we did was we linked the thickness to the x value. So instead of using thickness in the equation, in the case of air wedge, we substituted the x value, that is the distance from one end of the glass plate to the point where we are observing the fringe, so that that value can be directly measured by using the traveling microscope. A similar thing has to be done here. But here, instead of measuring the position, here we are going to measure the radius, or I can say that instead of using the thickness, now I am going to convert thickness into a radius format so that it is measurable with the help of a traveling microscope. So I am considering a random point over here, or I am considering the part of the film which has this thickness t, and the same t is available here, and from this I have completed the circle of which the lens is a part. That is your elementary school knowledge that every lens is a part of a circle, and then this length will be the radius of curvature of this lens. So this part will be the radius, and this part will also be the radius, and this is the thickness part, and if you subtract this thickness from the whole radius, this distance will be radius minus the thickness, and this distance will be the radius of the ring which you will be observing at this point. Due to this part of the film, there will be a ring which will be formed, and this distance will be the radius of that particular ring. Now, to this triangle, if you apply the Pythagoras theorem, you can write hypotenuse square equal to base square plus altitude square. On expanding this bracket value, you will get Rn square plus R square plus T square minus 2RT. Here we have R square. And this R square and this R square will cancel out. This 2RT and T square will come to the left hand side. So 2RT minus T square will be Rn square. But when you consider these two terms, this is a very big term, because usually the thickness will be very small. The thickness of the film is usually very small. So T is small, so T square will be very, very small. So you are subtracting a very small value from a big value. So this can be neglected. This T square part can be neglected. So you can write it as 2RT equal to Rn square. That is the radius of the nth ring. You have to square that term. You will get the term 2RT. So you can retain the 2T, that is Rn square divided by the radius of curvature of the lens. So 2T is Rn square by R, and that is why I retain this 2T over here. So instead of considering the thickness, you can just substitute this value over here. What is 2T? 2T is nothing but radius of the nth ring square divided by the radius of curvature of the lens, which is equal to, I am simplifying this, that is 2n minus 1 into lambda the whole by 2 mu. And from this expression you can write the radius of the nth ring square is equal to 2n minus 1 into lambda r divided by 2 mu, and from this you can directly write the equation for the diameter as well. Alright, I'll do it step by step. I'll do it from here. So I'm just taking the square root, so I'll get Rn equal to square root of 2n minus 1 into lambda r divided by 2 mu. Remember that this mu can be omitted because if it is there, mu value will be 1. I am now retaining it. That is your choice. So if we have the radius, then just multiply both sides by 2, you will get the value of diameter. So dn will be equal to, multiplying this side by 2, the 2 I am taking inside the square root, so I will get square root of 4 into this term, so that 4 and 2 will cancel out, so 2 into 2n minus 1 into lambda r divided by mu. The whole thing is inside the square root, or I can simply write it as dn is equal to square root of 2 into 2n minus 1 into lambda r if mu value is equal to 1. This is the expression for diameter of the nth ring. And what condition did we apply over here? We applied the condition for constructive interference. So at whatever, when you observe from the microscope, you will be seeing several rings, and whichever ring has this diameter or has this diameter which satisfies this condition, that ring will be a ring which is having constructive interference, or that will be a bright ring. So whichever ring that satisfies this condition, it will be a bright ring. So what can we do next? So instead of this n lambda, so here delta x we substitute as n lambda. So instead of n lambda, if I substitute 2 mu t plus lambda by 2 is equal to, instead of n lambda I am putting n plus half into lambda. What is that condition? That is the condition for destructive interference. Then 2 mu t can be arranged as n plus half lambda minus lambda by 2. I am writing it directly, that is n lambda. Then 2t can be written as n lambda by mu. So we know the value of 2t. What is 2t? 2t is nothing but Rn square by r equal to n lambda by mu. Then the radius of the nth ring square is n lambda into the radius of curvature of the lens divided by refractive index of the medium. Then radius is the square root of this term, that is n lambda r by mu. From this you can write the diameter. Diameter of the nth ring is square root of 4n lambda r divided by mu. How does this 4 come into picture? Multiplying both sides by 2. This 2, when I took it inside the square root, it become 4. Or if this mu value is 1, I can write it as dn is equal to simply square root of 4n lambda r. So whichever ring that satisfies this condition, so whichever ring that has this diameter that satisfies this condition, it will be a ring where destructive interference is happening, or it will be a dark ring. So I already told you, if you look at this condition, this thickness will determine what kind of interference is happening at everywhere, because this thickness is directly related to the radius of the nth ring. And why did we call it the ring? Because if we observe from the top, wherever the thickness has to be the same, if we collect all those points, or in other words I can say the locus of all the points where the thickness is the same will be a circle. So if you observe a fringe, that will be in the form of a circle. That is why I call the fringe as a ring. So instead of dark and bright fringe, I have to call it as dark and bright ring, which you can observe from the microscope. So this is the major conditions of Newton's ring. But now we have to discuss two major applications of Newton's ring. and one of them is to find out the wavelength of the light source which we are using. Simply by measuring the diameter, we will be able to know the wavelength of the light source that we are using. That is one application. And the other application is, if instead of air, if we are using some other material with some certain refractive index value, just by measuring the diameters, we will be able to find out the refractive index of the material. So first of all, I am going to find out the wavelength of the light source used with the help of Newton's law. So for that, what we have to do is that I am taking a random ring and measuring its diameter with the help of the microscope. We already know its formula, that is square root of 4n lambda r. I am considering the case of the thin film to be air, so the mu value is 1, so I am neglecting the mu part. So I am just measuring the diameter of a random ring, some arbitrary ring. So we see the pattern, we choose some ring to be the nth ring, and this is the diameter of the nth ring. So this ring will measure with this distance we will measure with the help of the travelling microscope. And after this, I will measure the diameter of another ring, which is some k rings after the nth ring. That is why I denoted the diameter of the second ring to be n plus kth rings diameter, dn plus k. I hope it is clear. First we will choose a ring from the pattern, and that will be the nth ring. Now I will choose some other ring which is k rings after the nth ring. So that will be a bigger ring. So I will measure its diameter, and that will be the diameter of dn plus k. And simply we can write it in the formula like 4 n plus k into lambda r. Instead of n, I will put it as n plus k. So omitting the square root, and I am squaring these terms and I am subtracting. What will we get? We will get 4n plus k lambda r minus 4n lambda r. And what this will be? 4n lambda r and 4n lambda r will cancel out, and remaining it will be 4k lambda r. The 4n lambda r and 4n lambda r will cancel, remaining will be 4k lambda r. And here we have the lambda which we require. So just rearrange that. So lambda will be equal to this term, that is dn plus k square minus dn square divided by, so retaining the lambda I am bringing down 4k and r. So we know the value of k, because from the arbitrary ring we are counting the number of rings, the kth ring. So we know the k, we should know the radius of curvature of the lens which we are using. Then we just have to measure the diameter of the two rings. The first arbitrary ring, that's the nth ring, and from that we are measuring the kth ring and the diameter of that particular. So just by measuring the diameter of these two rings, we can find out the wavelength of the monochromatic source that we use to form this pattern. This is the first application of Newton's law. And I am just marking this equation as 1. Let it be there. Now the second application is to find mu, and this was to find lambda. This was done to find lambda. Now we are going to find the value of mu. So instead of using an air film, like here first we were using an air film, that is how we did this experiment, and now instead of air I am choosing that there is some medium of refractive index mu over here. So what will be the formula for the diameters? You already know. So before omitting the mu, what was the formula? Dn was, so I am writing it as square. Dn square equal to 4n lambda r by mu. Alright. So I can't call this dn because dn we already used it. So I am called it as d dash. So d dash n square, that is 4n lambda r by mu, when we are using a medium of refractive index mu over here instead of air. And just like how we did over here, instead of some adjacent rings, we'll again measure the diameter of the kth ring. Remember, we are doing this time with the help of some material that has a refractive index that is not equal to 1. If it was 1, then we'll say that the case is that of air. Now it is not air, we have a medium that has a refractive index mu. Alright, and again I'll measure these two distances and I can just subtract them. dn plus k square, that is a dash, minus dn dash square will be the subtraction of these two terms. And what will that be? 4n plus k lambda r by mu minus 4n lambda r by mu. This is nothing but, again, what? 4n lambda r by mu and 4n lambda r by mu will cancel out. Remaining is 4k lambda r by mu. That is dn plus k dash square minus dn dash square. Can we do something with this? So I'm choosing this equation. Sorry, I call this equation as 1. Sorry, I'm going to call this equation as 1. That is dn plus k square minus dn square is equal to 4k lambda r. Now I am dividing the first equation with the second one. What will I get? Alright, so dn plus k square minus dn square, that is the left hand side. Right hand side is dn plus k dash square minus dn dash square equal to, right hand side of this term, 4k lambda r divided by 4k lambda r by mu. These things will be cancelled out and this will be mu. So simply the refractive index of the medium will be dn plus k square minus dn square the whole by dn plus k dash square minus dn dash square. So first we have to do this phenomenon. So if we want to measure the refractive index of a medium, first perform this part. Without the liquid, just measure the dn plus k and dn. Measure the diameter of the first nth ring and the n plus kth ring, and then do the same thing with the presence of the fluid of refractive index mu. Just by dividing these quantities, you can find out the refractive index of the medium that you have used as the film. So this is about the Newton's ring. I hope it is clear. Thank you.